All right, so we're finally ready to do it in the general case. So suppose you've got a general function such as f of x, and suppose I do the unthinkable, and I dare to think that it's equal to some polynomial. I dare to think that this could be possible. Could we do the same thing that we did on the sign to try to figure out what the coefficients are? As I said before, the key is in just figuring out what these coefficients are. If we can figure that out, we're done. And so we will proceed in the same similar way that we did for sine. First, we'll say, what does this thing tell us about f of 0? F of 0 would be a naught plus a1 times 0 plus a2 times 0 squared, on and on and on and on, leading to the conclusion that f of 0 is equal to a naught. So, in fact, I found this term right here. It's equal to f of 0. Okay, assuming that the function is defined at that point. There's a lot of little assumptions that I'm not going over right now, as to not to distract from the main idea, from the main and glorious idea that is the idea of Taylor polynomials. All right, so we got one down, and I'll make a little distinction here. Now I'm going after a1. To do that, I'm going to look at f prime of x. F prime of x is equal to a1 plus 2 times a2x plus 3 times a3x squared. In case you're trying to figure this out, I'm going here. This one gets killed. The x gets vanished when I take the derivative, so I'm just left with a1. The 2 comes over here. That's 2a1. And we drop down the power to 1. The 3 comes over here. That's how we get that, etc., etc. So it's 4a4 x to the third plus a5 x to the fourth. And of course, there's a 5 there. Let's do that correctly. 5a5 x to the fourth, and so on and so forth. Now, what happens when I plug in 0 here? I get that a1 is equal to f prime of f prime at 0. Well, the rest of the stuff is zeros. And so in that sense, I've accomplished one of the important things here. I found out what a1 is. Now I am going after a2. So I make a little distinction here, and I'm going to take this one, and I'm going to do a second derivative here. I'm going to take the derivative of both sides, and I'll have an expression for the second derivative. That will kill this one. That will leave this all by itself so that I could figure out what a2 is. Kind of like this. F double prime of x is equal to, now I'm looking at this line, and I'm going to take the derivative of that, the derivative of that, the derivative of that, all these. That's going to give me 2a2 plus 3 times 2 times a3 times x squared. No, just regular x. Or plus 4 times 3 times a4 times x squared plus 5 times 4 times a5 times x to the third, dot, 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 dot. I plug in 0 here, and everything vanishes except the 2a2, making it easy for me to figure out that a2 is equal to f double prime of 0 divided by 2. Okay, and so in that sense, I figured out what a1 is, I figured out what a naught is, I figured out what a2 is, and it was so fun. I'm going to go after a3 now. Of course, don't think that I'm going to be here for 5,000 billion minutes. In one or two more of these lines, I'm going to try to see the pattern, and you will see the pattern as well. And it will be beautiful, because then we don't have to do this every single time we want to find the polynomial expression of a function. Cheers to that. All right. I'm going to look at this line right here, and I'm going to take the derivative of both sides. That means I'll take the derivative of this. This will vanish. I'll take the derivative of this, the derivative of that, the derivative of that. And it will lead to something like this. F triple prime of x is equal to 3 times 2 times a3 plus 4 times 3 times 2 times a4 times x plus 5 times 4 times 3 times a5 x squared plus, of course, I can guess what the other one would have been, 6 times 5 times 4 a6 x to the third, dot, 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 dot. Okay, then we do the usual. By the way, you can see now why I was hesitant to multiply things like this. I could have said 3 times 2 is 6, 4 times 3 is 12, 20. That's what they tell you in middle school. Always simplify, simplify. I'm telling you not to. I don't want to simplify because I want to see the pattern. That idea that you should simplify is kind of a bad idea. It's what you get when your math teacher is actually the PE teacher in high school. Whoops. All right. That was really my math teacher, was the PE coach. All right. And look how I turned out. All right. F. Just kidding. I'm going to plug in 0 here, and I get 0 is equal to 3 times 2 times A3 plus 0 plus 0 plus 0. So I get that A3. This tells me that A3, solving for it here, I'm going to move the 3 and the 2 down here, will be F triple prime of 0 divided by 3 times 2. Or said differently, I get that it's equal to F triple prime at 0 divided by 3 factorial. And so that almost should be enough for most of us. Take a look at this. Take a look at what we've discovered so far. A naught is equal to F of 0. A1 is equal to, from here it's just A1, F of prime of 0. Of course, A2 is equal to F double prime of 0 divided by 2. A3 is equal to F 3 primes 0 divided by 3 factorial. In fact, we could have added factorials here on all of these, and it would be easier to see the pattern. So A4, rather than going through this entire song and dance here, we recognize a pattern. It would be the fourth derivative adds 0 divided by 4 factorial, and so on and so forth. A5 would be the fifth derivative. That's how you put fifth derivative at 0 divided by 5 factorial. And in fact, I've got the sought out formula, the pattern, the key to the universe here. All I do is take the nth derivative at 0 and divide it by n factorial. This, my friends, this is what you see in textbooks, in cheap textbooks that just want to tell you the answer in the formula. If you want trying to learn as little as possible, just learn this, that this is how you get the coefficients. And so this is the key to expanding any kind of function. As long as you have, notice what's required though, among other things, what's required is that you have derivatives. How many? A bunch of them, really, infinite many of them, so that you can evaluate them at 0 and then divide by n factorial. This is the key to getting the DNA for any kind of function. That, my friends, is amazing. And so once you have that formula, you can go on and play this game all day long. Let's say, for example, here, let's try out our new formula. In this case, what I want to do is maybe skip through a lot of this, because all this will always be the same. There's no sense in reinventing the wheel every single time you do this problem. Super, super important to see this, because this is how you derive the formula. Once you derive it, you own it, it's yours, and you can use it. So suppose we already own the formula. The nth coefficient is equal to the nth derivative evaluated at 0 divided by n factorial. And suppose that I want my f of x to be equal to e to the x, and I want to know e to the x, which is the exponential function. What is it equal to? Something plus something times x plus something times x squared plus something times x to the third plus something times x to the fourth, and so on and so forth. What are these things that go in here? What are the coefficients? Well, I know what a naught is. A naught is equal to f of 0. That would be e to the 0. That's equal to 1. So I know that e to the 0 is equal to 1, so that goes there, 1. Let's go red with all the coefficients. Gala. That was fun, right? How about a1? a1 is equal to f prime of 0 divided by 1 factorial. Well, what is f prime? I'm going to make a little chart here with all my primes. And the nth derivative at 0. So for 0, the 0th derivative is nothing, just e to the x. For 1, it's e to the x. The second derivative is e to the x. Well, this is so easy. All the derivatives are e to the x. This is a super good one to start off with because it's so easy. Then I want to know what is f of n at 0 divided by n factorial. So here I want to, so e to the 0 is equal to 1 divided by 0 factorial is still equal to 1. Now this one will be equal to e to the 0 divided by 1 factorial, that's equal to 1. This will be e to the 0 divided by 2 factorial, that's equal to 1 over 2 factorial. 3, that would be e to the 0 divided by 3 factorial, that's 1 over 3 factorial. E to the 0 divided by 4 factorial will be 1 over 4 factorial, and so on and so forth. So this is 1, this is 1, this is 1 over 2 factorial, this is 1 over 3 factorial, this is 1 over 4 factorial. And there you go. I figured out that what the right bridge is, connecting the e to the x to an infinite polynomial. E to the x is equal to 1 plus x squared over 2 factorial. I'm copying it and rewriting it so it looks pretty from here. Okay. Really, so it looks pretty. X squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial. Dot, 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 dot. There you go, my friends. E to the x like you've never ever seen it before. How amazing is that? Should we do that one more time? That was so fun. I think we should do it one more time. Suppose that we wanted the Taylor expansion. By the at for f of x, for f of x equals cosine of x. Okay. The key is to figure out all the derivatives. So f of x is equal to cosine of x. F prime of x is equal to negative sine of x. F double prime of x is equal to negative cosine of x. F triple prime of x is equal to sine of x. F fourth derivative is equal to cosine of x. F fifth derivative is equal to negative sine of x, and so on and so forth. So here's are my f primes. Here are my n's. 0, 1, 2, 3, 4, 5. And ultimately what I want is my f of n's at 0 divided by n factorial. So at 0, this is 1. 1 divided by 0 factorial is equal to 1. Here at 0, this is 0 over 1 factorial, that's equal to 0. Here, this is at 0, that's negative 1 over 2 factorial. Here, it becomes 0. Here, it becomes 1 over 4 factorial. Here, it becomes 0. And so on and so forth. So now, these are the coefficients. Cosine of x is equal to something plus something times x plus something times x squared plus something times x to the third. On and on and on. And what I've discovered here is that the first item is 1. Let's go red with the coefficients for consistency. This one is 1, this one is 0, this one is negative 1 over 2 factorial, this one is 0, this one is 1 over 4 factorial, and so on and so forth. And so we cleaned that up nicely for the grand conclusion that cosine of x is equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6th over 6 factorial, and on and on and on and on. There you go. The cosine of x written as a polynomial like you've never seen it before. You never thought the cosine could be written as a polynomial. In fact, it is. Infinitely long polynomial, also known as a series. So there you go. Amazing. Amazing. And so, by the way, there's another way that we could have done this. Earlier, here's an alternative way. Earlier we said that the sine of x is equal to, how do we, actually, the sine of x is equal to, let me think, x minus x to the third over 3 factorial plus x to the 5 over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, Duh, that's what the sine is. Now here's an alternative way to get to the same conclusion. Suppose we had already done that as we did earlier. We could have just taken the very elegant approach to this and said, you know what, since I already have the sine, why don't I take the derivative on both sides? And that would lead to the conclusion that derivative sine is obviously cosine of x. Now here the derivative of x is 1. So it would be equal to 1 minus 3 times x squared over 3 factorial plus 5 times x to the 4th over 5 factorial minus 7 x to the 6th over 7 factorial. Here, of course, I'm taking the derivatives of each one of these terms separately. Plus 9 x to the 8th over 9 factorial plus But amazingly, this thing cleans up nicely. You see, you have a 3 here and a 3 factorial there. This means 3 times 2 times 1, but the 3 can cancel. So really, you're just left with 2 factorial. Same thing with the 5 here. The 5 would cancel the 5, 4, 3, 2, the 5 part of that, and it would leave with a 4, 3, 2. So this could be x to the 4th. This could be written like this, 4 factorial minus x to the 6 over 6 factorial, and so on and so forth. So here would be another way to get to the same conclusion, the cosine being the even function with all the even ones. We could have saved all this work if we had just applied a derivative on both sides of the sine expansion. Okay. So beautiful. Now I think I should, so far we've done 2 or 3 examples with the expansions around 0. I think it's good if we do an expansion around something that's not 0. It's probably instructive to see here. So take an example take this example. F of x is equal to ln of x. Now I know that this looks like this, more or less. Well, they don't touch, not in the real plane. But you see, if I try to do this, a naught is equal to f of 0, ln of 0, I'm already in trouble. This is not going to be a real number. And so we have to abandon this idea and try to think, well, admit that not all functions have a polynomial expansion like that at any given point. However, we could shift our point of reference, our starting point, and say, you know what, I'm going to mimic this function, but I'm not going to start mimicking it at 0. I want to start mimicking it at 1. So I want to start here. This x equals 1, that's going to be my expansion. So first I'm going to match it there with the same value, then the same slope, then the same best fitting parabola, and so on and so forth. The expansion is going to be around x equals 1. For that, it's going to be almost the same as before, but slightly different. So it's going to look like this. We're going to imagine that f of x is equal to something plus something times x minus 1, because the expansion is going to be shifted to the right one, plus something times x minus 1 squared, plus something times x minus 1 to the third, and so on and so forth. So this is almost the same expansion, except everywhere instead of having x, you have x minus 1, causing the shift to go one to the right. Now f of 1 would be ln of 1 would be defined. And so what we need here is just the coefficients, sum a0, a1, a2, a3. And if you follow the same sort of logic, you'll see that the formula for this one is almost the same as before. It'll be an will be equal to the nth derivative of f evaluated at 1, because that's where we're shifting it to, divided by n factorial. So compare that with the other one. The other one was almost the same, except we were starting at 0. If you start at 1 here, if you started at 3, this would just be a 3. If you started at -1, this would just be a -1, etc., etc. In fact, you could think about it this way. You you can think about it this way. an is equal to f nth derivative at a all over n factorial. And then f of x would be equal to the sum of all the a_n's times x minus a to the nth power, as n runs from 0 to infinity. When such a beast is possible, this is how you do it. Almost identical to the examples we've been doing, with the only difference is that you evaluate it at a. And your powers are not powers of x, they're powers shifted, a units. Okay? So let's do this one. Let me think. Well, where do you start? Well, I'm going to make a little chart here and see if I can figure the pattern out. First of all, for the constant, I have just ln of x. What's the derivative? Sorry, ln of 1 would be the valuation at 1 divided 1 factorial. This is for a naught, or n is equal to 0. For n is equal to 1, I need the first derivative. That would be 1 over x. And evaluated, that would be 1 over 1 divided by 1 factorial. This was 0 factorial, same thing. For n is equal to 2, I need the derivative of that would be negative x to the negative 2. And evaluated at 1, that would be negative 1 to the negative 2. And then divided by 2 factorial. And then n is equal to 3. That would be 2 x to the negative 3. And I need that 2 times 1 to the negative 3 divided by 3 factorial. And then I need n is equal to 4. So this would be 3 times 2 times x to the negative 4. And that would be negative 3 times 2 times 1 to the negative 4 all over 4 factorial. And so on and so forth. So let's see if we can clean that up here. So for the first one, I'm getting ln of 1 is 0. Divided by 1, that's equal to 0. This one is 1. This one is negative 1 over 2 factorial. This one is 1 on the numerator, 3 on the bottom, because that 2 cancels the 3 factorial. This one is negative 1 over 4. I think I see the pattern. The pattern is 0, 1, negative 1/2, positive 1/3, negative 1/4, and on and on and on. Now I just need to add my polynomials. X squared. No, that's wrong. That would be at 0. X minus 1, x minus 1 squared, x minus 1 to the third, x minus 1 to the fourth, and with just pluses in between. Sorry, that doesn't look so pretty. I'll make it prettier. It would be equal to 1 times x minus 1 plus negative 1/2 times x minus 1 squared plus 1/3 times x minus 1 to the third plus 1/4 times x minus 1 to the fourth, dot, 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 dot. Boom. So this guy is equal to ln of x. Beautiful. That, of course, that's only for points near here. I can approximate it with polynomials here, and I can get it bigger and bigger and more better approximations the more I add on to this polynomial. Okay. And I have a suspicion that this expansion will be valid for x's that are here around here, but it won't cross the asymptote. So at some point we're going to ask, hey, which values is this expansion good for? When is this bridge good for? You say, oh, well, I think it will be good for all these ones, but I don't think you can get past that. So only like from 0 to 2, maybe something like that. That's like a whole different chapter, which that basically deals with that question: which x values is the expansion good for? Anyways, I think we'll stop here. It's a super crucial section. This is the first time we introduced this bridge in its full general sense. We did it a little bit before, but that was exploiting the geometric series. Anyways, we'll see you guys next time. Peace.